I'm going to start off by talking about the difference between 2.5D and 3D integration. So in 2.5D, there's no chip stacking involved. It's basically bare die, in some cases being assembled onto a silicon or glass interposer on a single plane. The device die are packed into a single package on that plane. The interposers themselves, the silicon or glass routing substrates, may or may not have TSVs or vias through them. If they do, it's typically the via dimensions are usually on the order of 10 by 100 or 20 by 150 micron. That's diameter by depth dimensions. There's typically low density RDL on the backside of the interposer with flip chip pads on the front. Sometimes and either flip chip pads or bumps on the backside of the interposer so that it can be assembled onto the next level substrate for packaging. In a 3D structure, you have chip stacking with TSVs and one or more die. The TSVs, as Robbie mentioned earlier, are electrical, typically electrical, but they could also be thermal vias. That's also being used in the industry. And they provide a conductive path from the front side of the chip to the back side of the chip. So signals or power or grounding can come in directly through the chip vertically and allow one to stack chips vertically for communication between the chips. The TSVs are electrically isolated from the substrates themselves by deposition of a dielectric layer to keep it isolated. And then typically they're either copper or tungsten, although there are some that use polysilicon for the conductive layer. There are two ways to fabricate TSVs that have been adopted in the industry. The first one is vias last, so that would be wafers coming from the CMOS foundry and TSVs being inserted into the wafers after they leave the foundry. This requires designing, again, getting back to some of the things that Robbie pointed out, at the design phase, if you know you're going to go this route, where are you getting your die, and does the design require a TSV? And if so, you need keep out zones because for inserting TSVs after they leave the foundry, the process is required to do that. You cannot have CMOS metal in the path of where that TSV is going. The other option for TSVs is to get them made at the foundry for those that do have a TSV process available. This is called a vias middle process, and that the vias would be created after the transistors, but before you do the rest of the back end of line routing. And so this requires, when they come out of the foundry, only that you do what's called wafer finishing. And that means thinning the wafer from the backside to reveal the blind TSV that's already there, and then making any redistribution layer or backside contact pad interconnect so that it can be assembled onto another substrate. There are three other types of architectures for 3D integration that you can consider. In the case of the far left image, the system on chip, that's typically a combination of functional blocks all designed into one chip, but that requires some trade-offs in design and your performance, because you have to go. If it's a mixed signal chip and you need analog and digital there, then you're doing some trade-offs in the design space because you're trying to put it all into one foundry process. As was mentioned earlier, a system in package much more resembles a system on motherboard. It's just shrunk down to a smaller package level. And again, here what you're gaining is you get to take the functional blocks, disaggregate them, and build them in their best of breed processes, and then reintegrate them on one or more chip carriers or substrates. And moving to the middle, the monolithic 3D ICs. This is a process by which you're basically building transistor level layers directly on top of each other. It involves a process of stacking, aligning, and connecting leading edge transistors on top of each other to form what's called a monolithic 3D chip that uses standard vias that can provide up to 10,000x more connections. So this is a very high density solution, but does not have applications for, doesn't apply to every application that's out there. There are some limitations in implementing this solution. There are thermal budget constraints for the anneals that are needed. There's also some deposition and epi challenges that people have to work through. And then on the far right is a 3D stacked IC, which I think is a little more common to see out in the industry. The biggest application space that's driven this in terms of its commercial availability in a product is the memory stacks, where you're stacking die of same size on top of each other to create a memory module. Many of you may have heard of hybrid memory cube. That's just another iteration on that. And the key here is that you have die with TSVs in them that are stacked up to create multiple die stacks and to create a new module that way. Some of the emerging applications for 3D stacked IC, I should mention, are for advanced imagers and anything where you're dealing with a pixelated device, whether that's a display type device or a sensing element, where you would want, you could provide an interconnect per pixel below it that enables you to put more processing power directly beneath that element. This we put this illustration in here from Heterogeneous because I think it's a good representation. If you look at the advanced packaging technology roadmap, it covers a pretty good range of all the advanced packaging technologies, many of which we have discussed here earlier. But it shows them relative to each other, but also in terms of the I/O pitch and the I/O density. So I/O pitch on the x-axis, I/O density on the y-axis. And if you start at the bottom and the bottom left, where you have the largest pitch and the lowest density, you'll note as you move up that graph to the different colored circles, you're moving from different types of interconnects to realize those packaging solutions. So in the bottom left, it's BGA balls, which are very, very large. Then you move up into the territory at fan out with bumping, and that takes you all the way up to the gray circle where you have 2.5D silicon interposers. And then at some point you reach, in applications where you need to go to higher density, smaller pitch, and that takes you into the regime of micro bumps and copper pillars. And then eventually you get to just micro bumps for an embedded silicon bridge implementation. And then finally, if you get away from using bumps altogether, you go to the hybrid bonding, which is another integration technology that relies on oxide to oxide bonding. And so on this slide, we're just showing some of the advanced interconnect implementations that I touched upon in the Yole graphic. Moving from the left column to the right column, we're showing examples of wafer level packaging where you have redistribution layer in copper and bumps. So this is for a fan-in example. The middle image in the left column is copper pillar, and this was actually for an I/O for silicon photonics. In the bottom left corner, showing an example of flip chip multi-chip module assemblies. So these are detector modules of various sizes that were built with eutectic solder flip chip bumping technology. In the center column, showing an example of a silicon interposer-based package for an embedded compute module, where the interposer had high-density routing on the front side, some through silicon vias, and some low-density routing and off-chip pad on the back side. And then at the bottom of the center column, there's actually the bottom two pictures on the center and right column are examples of some micro bumping. One is sub 20 micron pitch for infrared detector application, and the other is for a demonstration on thermal compression bonded die stacks for 3D integration flow that then was actually implemented in the next image up for a 3D IC via implementation. And then you can see in the upper right corner another example of 3D IC where, again, TSVs through an actual active chip and then assembly of component on the bottom, as well as the larger bumps on the larger bumps on the top are actually the backside, and that was assembled onto another substrate. So all in all, if you're looking to navigate these waters in terms of finding the right Hi-Rel packaging solution for your application or for your needs, Micross is there to help you. It can either be a collaboration between us and your company, a la carte, where we provide the expertise that you need to realize the solution. For some of the aspects listed here in the sub bullets under collaboration, or you can engage with Micross as just a full turnkey service provider.